All right, thanks all for coming along. My name is Ian Robinson. I'm an engineer at Neo Technology. I've been there about 3 years. I've spent quite a bit of time working with our users and our customers, helping them design and develop graph database applications. But today I'm developing the core product. I'm talking today about designing and building a graph database application and about a couple of the strategies that I employ when I'm building that kind of application. Strategies for designing a graph data model, your application's graph data model, and the queries that you'd execute against it. And strategies for testing that model, for writing unit tests and being able to test the model and test the queries so that you're confident it does exactly what you want. So the motivation for the talk really is, well, it's my experience of building software over many years and doing that in a kind of iterative and incremental fashion. And a couple of the concerns that I have, whatever technology I'm using. So when I'm building software, there are a couple of things that are very important to me. One of them is that I want the software itself, the code, the data model, the queries that I execute, I want it to be expressive of the problem at hand. I want to be able to see the business problem in the code, see the terminology, see that reflected back to me, so that I can easily make sense of it, and so that other people working on the project as well can easily make sense of, well, this is what we're trying to solve, and this is how we're going about it. So one of the ways in which we do that today, we apply things like domain-driven design. We use subject matter experts to help us identify the terminology that's important to us, and then we can bake that terminology into our code, into our data model, into our queries. Okay, so it makes it expressive of the problem at hand. So that's one of the things that's important to me. The other thing is, I want to be confident that I can evolve my application over time. If it's successful, it's likely it's going to survive for a long period of time. And things change. The business environment changes. People come up with new requirements. I want to be confident that the application I'm developing can be evolved very, very rapidly in order to satisfy those new requirements. And one of the ways in which we do that today is to use things like unit tests. Write lots and lots of small tests. We apply them in an iterative and incremental fashion. And they give us a good bedrock, a kind of bedrock of assertive behavior that gives us the confidence to change the code as new requirements emerge. It gives us the confidence to move forwards very quickly. So these are the couple of things that are very important to me. And when I started working with Neo4j, I wanted to ensure that I could work with Neo4j using these kind of strategies and techniques. So these are the things I'm going to be talking about today. I'm going to spend the first half really talking about how we would go about designing a data model and the queries that would execute against it on behalf of a particular application. So you've chosen to use a graph database, to use Neo4j to back your app, whether it's a web app or a mobile platform or a desktop app. You're going to need to develop your own graph data model. You'll employ things like nodes and relationships, properties and labels. They're the fundamental building blocks, but you're going to apply those in order to develop your graph data model for your application. How do we go about doing that? And then the queries, you're going to be able to create data and, importantly, query the data in order to be able to ask those really interesting questions of your domain, that underlie your application. The second half of the talk, I'll be talking about how we actually go about testing that data model. How can we develop this in a test-driven fashion, using unit tests to ensure that it's correct and to give us that bedrock of assertive behavior. And in the middle, I'll talk very, very briefly about a number of the different architectural options that are available when you're using Neo4j and how that influences the way in which we actually go about testing the stuff. Okay. So graph data modeling. The first thing that I want to say is it's a well-understood point. It's a relatively trivial point. But if we're developing a model, we're creating a purposeful abstraction of our domain, of the things that are important to us in our domain, in order to satisfy some end-user or application goals. We're not trying to create a transparent window onto reality. And we say that graphs are everywhere, graphs are enormously expressive, but they have to be expressive of the problem at hand. We're not just trying to reflect the world as it really is, as though we could do that. So the point is we need to understand what our motivation is here. What are those end-user goals or those application goals? Once we've got a clear understanding of that, we can begin to translate them into our data model. We can drive out the data model and drive out the queries based on our understanding of these goals. So the diagram here from Wikipedia are the steps that Euler employed when solving the 7 bridges of Königsberg. He takes a huge welter of information. The problem he's trying to solve is it possible to cross each of these bridges or to navigate around the city of Königsberg, crossing each bridge only once? It's a huge welter of information there, but a lot of it Euler eliminates almost immediately. He eliminates all the noise and creates a very purposeful abstraction of the stuff that's important to him in order to be able to create a model that helps answer that question. And we've got to do exactly the same when we're developing our own applications. So what I'm going to do, I've got a little walkthrough, really, of some of the steps that I'd employ when I'm developing an application. And so I've got a little sample scenario, and that's of us creating a little knowledge management app. Right, so imagine we want to capture some information about people and the companies they work for, and some of the skills that they possess, and their proficiency with different skills. And then that allows us effectively to identify my semi-professional, my professional network. People who share skills, share my interests. Particularly if you're working in a large organization, you want to be able to identify those other people in the organization who share your skills so that you can create interest groups, you can reach out to them if you've got a technical problem, you can identify the right person to help solve your problem. Perhaps you're starting a new project, you want to staff that project. Again, you want to be able to identify the people who have the right skills, and perhaps people that you trust, people that you've worked with, or people who've worked with the people that you've worked with. So that's the basis for my little sample, or my example app here. And I want it to be cross-organizational. I actually want to capture information about people who work in multiple or different organizations and be able to query across that. So I'm saying the first thing that I need to do really is to understand from the outside in, from the top down, what is it that we're trying to achieve? What are those application goals or those end-user goals that we're trying to meet? And one of the ways in which we can express that is using things like agile user stories. They describe from the point of view of a consumer of this application or a user of this application what it is that they're trying to achieve. So typically I'll start with some natural language expression of the goal at hand. I've got a very simple one here. As an employee, I want to know who in my company, the company that I work for, has similar skills to me so that we can exchange knowledge. This is one of the first requirements that I'm going to try and satisfy as I'm building out my application. And there's probably likely a whole backlog of these kind of stories that we're going to play over a period of time, this iterative and incremental development process. But I'll take something like this, agile user story. It's a description of what it is that we're trying to achieve. This is the goal. Okay. And the first thing I'll do is to drill into it and try and identify, well, what kinds of questions would I have to ask of my domain in order to be able to satisfy this end user goal? So the story is what we're trying to achieve. The questions that we would want to ask of our domain help indicate how we would go about satisfying that goal. Okay. So all I've done, I've taken that story and I've simply turned it around a little, turned it into a question. The question that I would have to ask of my domain in order to satisfy this goal. So which people who work for the same company as me have similar skills to me? Now once I've got that question, I can begin to identify some of the things that I'm interested in. Some of the things in my domain that are of interest to me. So I've got people, companies, and skills, or in the singular, person, company, and skill. Okay. So these are some of the entities in my domain that are particularly important to me when I'm developing an application to satisfy this story or to meet this goal. Having identified the things that I'm interested in, I can then begin to understand, well, how are they connected? How are they related? What's the relationship between some of these entities? A person works for a company, and a person has a skill or has a set of skills. Okay. So again, I've taken the natural language representation of that question, and I've just identified some of the things I'm interested in and the ways in which those things are connected. Now, I've kind of cheated a little here. I said person has skill, skill. You can probably see where I'm headed with this. These are likely going to be relationship names. And what I've done here is kind of right-size the relationship name here between the person and their skill. And if I just use the word has, well, that's a very, very general, very generic kind of relationship between two things. I can have skill, I can have a job, I can have a wife, I can have children, I can have a fear of clowns and balloons. If I used has throughout my domain, then the kinds of questions I want to ask of that, I'd end up exploring a huge portion of the graph when in fact what I really wanted to do was target that question far more specifically. So even from the outset, I've started thinking about the ways in which things are connected, but I've also started thinking about how can I right-size some of those relationship names. Okay. Because choosing the right relationship name, this is really the royal road into the graph. It will give you a very efficient query, finding just the stuff that you're interested in and ignoring everything else if you can choose a relationship name that, that is very specific to your use case, is very aligned with your use case. Okay. So I've taken the story, I've turned it into a question, I've identified some of the things that I'm interested in and the ways in which they're connected. I can then take these two expressions here and I can translate them into cipher paths. So, as I say, I've already identified what are likely candidate relationship names, and the things at the either end of the relationship are likely candidate labels for some of the nodes in my graph. Okay. So I can take those two expressions, and I can turn them into a couple of cipher paths. So we can see that a person works for a company, a person has a particular skill, some particular skill. Okay? So we've got parentheses to represent the nodes, and then dashes and greater than or less than signs to indicate the relationships and the relationship direction. And between the square brackets, we've got the relationship name itself. Okay? So candidate labels, candidate relationship names. Now, I can actually consolidate these two paths. It's something that, Max was going in the other direction in his talk. He was taking a single path and breaking it up into a couple of comma-separated expressions. I just want to show that here, actually, I can consolidate these two expressions and come up with a single cipher path. A person works for a company, and a person has a particular skill, some particular skill. So this is a cipher, an ASCII art representation of a path. It's effectively us drawing this picture. Okay, a person works for a company, has a particular skill. And you can see the labels that I would attach to the nodes here. So what we've done here, we've effectively come up with a prototype path for our data model. This is effectively, if we can stamp out multiple instances of this path when we actually create our data, we will have identified the things that we're interested in and the ways in which they're connected, and we've derived all of that from our user story and the questions that we want to ask of our data. So at this point, effectively, I have a prototype for my data model, insofar as it helps satisfy this particular requirement. Okay, there may be other requirements coming on further down the line that would encourage us to modify or change or enrich this structure, but this is a foundational structure for our data model. So if I can go ahead and actually stamp out instances of that path over and over again, we might come up with something like this. This is a very small sample data set, but this is an example of the kind of graph that we'll probably end up creating when we're capturing user data. So you can see they've got a company here, 3 people who work for that company, and then a number of different skills that those people possess. And what you'll see is that over and over again, we've got instances of this path structure. Ian works for Acme and has the skill Java. Ian works for Acme and has the skill C#. Lucy works for Acme, has the skill Java, has the skill Neo4j, and so on. Multiple instances of this path structure over and over again inside of our sample data set. So I'm not going to talk about how we would actually go about creating that, how we populate the graph in the first place. Instead, I'm going to concentrate a little on how we go about querying it. Given that we've derived our data model or our graph structure, we then probably want to go back to our requirement, go back to the question, and work out, well, how would I go about querying this in order to satisfy this end-user goal? So let's go back to the question. Which people who work for the same company as me have similar skills to me? So in order to answer this question, I'm going to have to find some patterns inside of my graph, inside of my data set. So I'm going to be looking for a specific pattern. And this is the pattern I'm looking for. It's a little diamond-shaped pattern. Somewhere in the graph, there is hopefully a node that represents me. And I'll be connected to a particular company, and I'll be connected to one or more skills. I'm connected to a skill here. What I'm looking for are people who also work for the same company and have the very same skill, who are connected to the very same skill node. And I'll be looking for multiple instances of this pattern. Every instance anchored on the node that represents me, but hopefully matching different colleagues and different skills, all of whom are connected to the same company node. So I'm looking for multiple instances of this diamond-shaped pattern. So that's the pictorial representation. but I can turn that again into a cipher path or a couple of cipher paths that represent the pattern that I'm looking for inside of my graph. So this is what the cipher query looks like, the translation of that question into a cipher query. And I'll go through it step by step or clause by clause. So the first clause here is that match clause. This is the pattern. The match clause helps specify this is the pattern that I'm looking for inside of my graph, inside of my data set. And so what we have here are a couple of paths separated by a comma that help express this diamond-shaped structure. This is the pattern that we're looking for inside the graph. There's a node that represents me. It will be a node that's labeled person, and I'll have a particular skill, and I'll work for a particular company, and I'm looking for other nodes that are connected to the very same company node and connected to the very same skill node, and we'll call those my colleagues. Okay? So a couple of paths separated by a comma, and that helps express this diamond-shaped pattern. The top path here is the left-hand side of the pattern. Me works for a company, has a skill. The second line here is the right-hand side of the pattern, colleague who works for the same company and has the same skill. Then in the where clause, we're actually binding this pattern or anchoring this pattern to one or more specific nodes in our data set. So I'm saying, look, there's a node that represents me. It will have been labeled person. I want to find nodes that are labeled person where the property name or the property name has the value whatever I supply to the query. This is a parameterized query. But if we supplied the name Ian, then we'd be looking for nodes that are labeled person that have a name property whose value is Ian. And that will help anchor that pattern inside the data set. Okay? And then we can flex that pattern around, seeing whether it matches other nodes that are connected to that anchor node. And they're the things that we're going to return when we generate the results on behalf of the client. Okay. So search nodes, labeled person, matching on that name property. And then the return clause, here we're simply creating a projection of the data that we found on behalf of the client. So I could choose to actually return all the nodes and the relationships that we find, but in fact what I've chosen to do here is for every colleague that we find, I'm taking their name property and aliasing it as name. So I'm creating a kind of tabular structure here. Then I'm counting all of the skills that that particular person has in common with me. So remember, some of these people may have more than one skill in common with me, so we'll actually have multiple matches on behalf of that person. We'll match that diamond-shaped pattern several times on behalf of that colleague. So what we'll do is count up the number of skill nodes that we've matched on behalf of this particular colleague. Kind of doing an aggregation here, an implicit aggregation. So we're counting the number of skills they have in common, and we're aliasing that as score. All right, that's their score. Now, it's interesting to know how many skills somebody has in common, but it's also interesting to know which specific skills that person has in common. So the collect function here is generating a comma-separated list of all the particular skills that that colleague has in common with me. All right, so we've got their name, the number of things they have in common, and then a comma-separated list of all those skills themselves. And then we're ordering the results based on the score, highest score first. So if we were to execute this query against that little sample data set I showed earlier, these are the matches that would occur. So we're anchoring it, we're finding a node that represents me, that represents Ian, so that's the value that we're supplying to the query. And this is our first match. Ian works for Acme and has the skill Java. Lucy works for Acme and has the skill Java. So that's that first diamond-shaped match. Second match. Again, Ian and Lucy work for Acme. This time they both have the skill Neo4j in common. And then our third match, Ian works for Acme, Bill works for Acme. Ian and Bill both have the skill Neo4j. Okay. So here in the browser, we've got a little, there's our sample data set. If we actually run that query, I don't know if you can see at the back. Lucy has two things in common, Java and Neo4j. Bill has one thing in common, one skill in common, which is Neo4j. Okay. Exactly those results. So what have we done? We've started with an end-user requirement, some natural language description of what it is that we're trying to achieve. And we've drilled into it, and we've tried to ask or discover what kinds of questions would I have to ask of my domain in order to be able to satisfy this end user requirement? And then given that question, we've unpacked it a little. We've identified some of the things that we're interested in, the entities in our domain, and the ways in which those things are connected. And they became candidate relationship names and candidate labels that we would attach to some of the nodes in our graph. And based on those expressions there, we were able to derive a path, a kind of prototype path, that is effectively the basis for our data model. So we derived that path from our user story. We've created a little sample data set, and then we've gone back to the question, and this time we've reformulated the question as a query. Okay? And we've decided we needed to match or find this diamond-shaped pattern inside of our graph. Now, the interesting thing here is that the paths here in the match clause, I've got two paths here, look very similar to the path that we used to create the data in the first place. So this helps emphasize the point that when we're creating a data model and creating the queries, these are two sides of the same coin. We're designing for queryability. If we're deriving the data model from the questions that we want to ask of the domain, then the paths that we use to create the data in the first place will look very similar to the paths that we use to interrogate the data when we're trying to satisfy that end user goal. So it's often a good test of whether your model is a good model if a lot of the paths in your queries look very similar to the paths that you've used to create the data in the first place. Okay. All right. So, that was just one requirement, one very simple requirement. Typically, as I say, there'd be a whole backlog of those things, and we work through them, we develop this stuff, iterative and incremental development. And as I learn more about the domain, it may be that I add additional kinds of nodes, additional labels, different paths that I would use or discover through the graph. But I'm quite happy to work on a requirement-by-requirement basis, and in particular to align a lot of those relationship names with the use case at hand. You can specialize the graph for different use cases and introduce lots of different relationship names in order to satisfy different end-user requirements. You can connect nodes in lots and lots of different ways. So we're capturing data about people, about the users of our system, about companies, and about their skills. But as we apply different use cases, it may be that we need to connect those entities in different ways. And we can introduce different kinds of relationships with different names in order to satisfy those end-user requirements. And then the queries that we write will just see the graph that is structured in a way that's appropriate for that query. Always designing for queryability, and being able to supply specific relationship names in the query effectively helps us filter or create a projection of the graph that helps satisfy that particular goal at hand. Yeah. All right. So that's designing the data model, designing some of the queries. But as I'm doing this, I actually want to do it at the IDE. I actually want to write code, write unit tests that help express my understanding of what it is that I'm trying to achieve and create this bedrock of assertive behavior. So typically I'll do this in a test-driven fashion, unit test by unit test. And the reason I do this, well, I want some rapid feedback. I want to be confident that the model I'm developing and the queries that I'm developing are fit for purpose, that they do exactly what I expect of them, and I want to get the feedback as quickly as possible regarding that. I want to document my understanding of the domain. Okay, it's nice to have these natural language expressions of what it is that we're trying to achieve, but as a developer, I also want to bake that knowledge into the code that I write. And one of the best ways of documenting that is to write unit tests that express this is what I'm trying to achieve and this is how I've gone about satisfying that goal. And particularly if you're dealing with a domain where there's lots of corner cases, lots of variably structured data, where no two things need look exactly alike. And if there are lots of exceptions or corner cases, then it's great to write lots of unit tests that help express your understanding of, well, these are all the exceptional circumstances, these are all the weird parts of my domain. Okay. And then finally, lots of unit tests provide me with a good regression test suite. This is something that gives me the confidence to evolve my application very rapidly. A new requirement emerges or a need to change parts of the app. I know that I can go ahead and make the changes in the code or make the changes in the data model, rerun all of my tests and find out, well, am I continuing to satisfy all my existing obligations, or have I broken some functionality? Again, rapid feedback gives me the confidence to move forwards very quickly. So the strategy that I typically employ is to encapsulate the queries themselves in some kind of object, the object under test. So we're going to develop objects that encapsulate our queries, whether we're writing them in Cypher or whether we're using some of Neo4j's other Java APIs in order to query the database. And then within each test fixture, test fixture might comprise a number of tests, but within each test fixture, I'll create a very small, well-understood data set that I control, a kind of lightweight, in-memory database that I'll populate with a small amount of data, just enough data to express the particular scenario that I'm working on at that point in time. And I'll inject that data or that database into the object under test. And then I can exercise the object under test, exercise the query. And because I've controlled the data, I know what results I expect to get back. So I can create some assertions that assert those results, and I can be confident that I'm getting back exactly what I expected, nothing more and nothing less. So I'm going to show you some examples of those unit tests and those unit test fixtures. But the actual strategy does depend slightly on the way in which you're employing Neo4j in your app. So it depends upon the application architecture. So, I mean, you may be familiar with this, but in fact, I'll briefly summarize. There are several different ways in which you can use Neo4j in an application today. It started life over 10 years ago as an embedded graph database. You can still run it today as an embedded graph database. This means that you host the database inside your own Java process. You host the database engine inside your Java process. You stop and start it. You control the database from your code. But that's not our experience today of most other database products. Typically, we expect a database to be somewhere else over the network, and we're just going to communicate with it over the network. We don't want to embed it in our process itself. So most people today actually run Neo4j as a server product. We've talked about that a little bit earlier on in some of the other sessions. Effectively, the server product is a wrapper. We've created the server infrastructure that wraps an embedded graph database instance. It hosts it out there on the network, and then your client communicates with it over HTTP. We provide a REST API, and you exchange JSON formatted documents with the server in order to query it or to create data. And that's our kind of vanilla API, our vanilla remote API. Then you can go one step further, and you can actually incorporate some of your own code inside the server. You can create the equivalent of stored procedures, bits of Java code that sit inside the server that might do some arbitrarily complex calculation or complex traversal and generate the results on behalf of the client. So these are our three options. Running it as an embedded graph database. Now, embedded, not in memory. Okay. So even the embedded graph database makes all of that data durable on disk. When you create data, it's always saved, it's always persisted on disk. Okay. But the advantages of using embedded are that you have access to not only to Cypher, but also to a large range of other Java APIs. If you absolutely need to, you can get a lot closer to the data in its raw form as nodes and relationships and properties, and you can use those Java APIs to manipulate or query the data. Server, as I say, exchange JSON formatted documents over HTTP. Each server wraps an instance of an embedded graph database. We've created the server infrastructure on your behalf. And then finally, server with extensions, where you can write some additional code that sits inside the server that allows you to do arbitrarily complex operations, but also allows you to control the request and the response format. So if you're running the vanilla REST API, then all of those documents they're exchanging talk in terms of nodes and relationships and properties. But if you're writing an extension, you can actually control that response format and the request format. So the data you return might actually look far more like your domain, might talk more in terms of companies and users and skills. And you completely hide the fact that you're using a graph under the hood. Okay. So I've got some examples of how we would develop against an embedded graph database, and then how we would go about developing one of those server extensions. And in both cases, the example is exactly the same. We're taking the requirement that we looked at earlier and the little sample graph that we looked at earlier, but now we're actually going to develop the query in a test-driven fashion. Okay. So this is embedded, running in embedded mode. And this is what my unit test fixture will look like. Okay, so we do some setup and some tear down after every test. And I'll just walk through that in a bit more detail. Okay. So before every test, this init method will run. And here we're creating a very lightweight, in-memory version of Neo4j that we can populate with some data. And we're assigning that to a member variable. Okay. So I've created an in-memory version, and now I'm populating it with a small amount of data that I control that allows me to express the scenario at hand. And then I'm creating the object under test. So I'm going to create a colleague finder object that encapsulates my Cypher query. And what I'm doing here is injecting the Cypher execution engine into that object under test. Okay. And again, the object under test I've assigned to a member variable. And when we tear down after the test, we just clean everything up. We just tear down the database, shut it down cleanly. Okay. So you see here I was using something called Test Graph Database Factory, and it allowed me to create a new impermanent database. Okay. This is a lightweight in-memory version of Neo4j that we use internally within Neo when we're developing parts of the product. It's an in-memory version of Neo4j. It's purely for testing purposes. Okay. It's not for production use. People sometimes say, well, I want an in-memory graph database. Can I use this? Well, no, we don't warrant it for production use. But we do make it available in our test jar. You can download it, and you can use it in exactly the same way that we do. And it's just a little quicker in terms of setting up and tearing down. It's a fully featured version of Neo4j. We've just effectively stubbed out the file system at the bottom. Okay. Right. This is that populate method. So I created an in-memory version of Neo4j. Now I populate it with a small amount of sample data. Effectively, I build up that little sample data set. And again, I'm doing that using Cypher. Once I've done that, I can then start writing the tests themselves that exercise my colleague finder. So here's my first test. My colleague finder should find colleagues with similar skills. Okay? So remember, I created the object under test when I created the test fixture. Now I'm going to call one of its methods, find colleagues for. Now at this point in time, we actually haven't written the colleague finder, but we're writing the first unit test that expresses our intent to call this method, find colleagues for. And I'm going to pass in the value Ian. That gives me back some results. And because I've controlled the data, I can control the assertions. I expect the first result to be Lucy, because she had more in common with me than anybody else, and the second result to be Bill. And then finally, I assert that there is no more data returned. Okay, so this is a very important assertion. It's great to get back the data that you did expect. It's not so good to get back some data that you weren't expecting. So I want to be confident that the query works as I expect, and that there are no more results that are returned, given that sample data set. Okay. So that's my first test. Now I can actually go about developing the colleague finder itself. So this is the skeleton for that colleague finder. Here in the constructor, remember in the setup, we injected the Cypher execution engine into the constructor. So we just save that, we store that in a member variable, and then we can start working on our find colleagues for method. We can start fleshing out the implementation there. And that's it here, the find colleagues for. So I've taken my query, the query that we worked on earlier, that we looked at in the first half of the talk. It's a parameterized query. There's the Cypher query. I supply one of the parameters. So we were passing in the value Ian in our test. That was that name parameter. I'm actually creating a map, and that allows me to parameterize this query. And then I use the execution engine to execute the Cypher query and pass in those parameters, right? And then we just grab hold of the iterator of the results. Okay. So that's it. Everything hopefully works as expected by this point. We've got a test that turns green. We're confident that our query works as we're expecting, and that we're getting back the results that we expected. Now, it may be I want to introduce additional tests that test some of the corner cases, if there's some exceptional data. What happens if there are null values, if for some reason somebody's name property doesn't exist. I probably want to write additional tests that test all of that behavior as well. And I just go on in this incremental, iterative fashion. So that's testing embedded. It's slightly more tricky when testing server or testing server with extensions, but I'm confident you can still do it test by test and in a test-driven fashion. So it's the same scenario as before, but this time we're going to create a server extension that hosts an instance of our colleague finder. And then a remote client, some REST client, doesn't matter what platform, can invoke that extension, can just post some data to a URI, and we'll execute that query, generate the result, and send it back as JSON to the client. So this is what an unmanaged extension actually looks like. This is what you have to develop if you want to create these extensions that sit inside the server. And an unmanaged extension is simply a plain old Java object that just has some additional annotations, some JAX-RS annotations. So effectively what we're creating is a RESTful resource, something that can be hosted at a particular URI and can respond to requests that come in over HTTP. Okay. So what we've done, we've used these JAX-RS annotations, both on the class itself and on a particular method. These belong to the JAX-RS spec. But all they help do is intercept or listen for HTTP requests and to dispatch specific requests to an instance of this class and invoke a particular method. So what we're saying here is that if there's a request that is sent to a URI whose path begins /similar skills, then we'll dispatch to an instance of this class. We'll create an instance of this class, and then we will dispatch to it. And then further, we're annotating it further here, saying, well, if it's, for example, a GET request to similar skills /Ian, then we will invoke this method. And we will take whatever's supplied here, this parameterized part of the URI, and we'll actually pass it in as a parameter into the Java method. Okay, so that's all these annotations are doing. They're helping map HTTP requests and parts of those requests to an instance of this extension and invoke a particular method. Now, there's one other annotation here, this @context annotation. And we've put this on the constructor itself. So for every request that's dispatched to this extension, we'll create a new instance of the extension, a new instance per request. And the @context annotation here allows us to, helps tell the server infrastructure, I want you to give me an instance of the embedded graph database that's at the heart of that server. Or in fact, here we're saying, I want you to give me an instance of a Cypher executor that in turn wraps a Cypher execution engine that operates against the embedded graph database. So even though we're building a server extension, in fact, within the implementation of that server extension, we can grab hold of the embedded graph database that's hosted by that server. And these annotations will just tell the server infrastructure to give us that stuff, to give us the embedded graph database. So from this point on, it's very much like developing against an embedded graph database instance. All right. So here I create an instance of my colleague finder, the stuff that we tested earlier, and I'm injecting the execution engine here. All right. So that's the server extension itself. Within this method, we're invoking our colleague finder, much as we did before, but then we're taking the results and we're just formatting them as JSON and creating a 200 OK HTTP response together with that JSON formatted body. So a very trivial implementation. Okay, so I've shown you the implementation up front, but I would still actually drive out that implementation using unit tests. This is what the test fixture looks this time round. Again, we've got setup and tear down. But whereas when we were testing embedded, we created a little lightweight in-memory version of Neo4j, here we're creating effectively a lightweight server and starting the server up. And then that allows us from within our test to communicate with the server over HTTP. So I'm using this community server builder to create an instance of a server and to host an instance of my extension inside of it. I start the server, and then once the server has started, again, I can populate it. I can populate the embedded graph database inside of that server with some sample data. So again, I control the data. And in the teardown, once again, I stop the server and clean everything up. Right. So again, the details, if you want to get hold of the community builder, or that server builder, again, it's just a helper class that allows you to create servers, configure them for test purposes. Right. So this is actually what one of the tests themselves look like. Now again, with the embedded graph database, we were able to go direct to our colleague finder. Here we're going a little bit more around the houses because we're going to invoke our extension over HTTP. So we create an HTTP client, and then we make a request. So a request to localhost 7474, colleagues /similar skills /Ian. So this particular part of the URI towards the end here, this is going to help dispatch that request to our extension. We grab hold of the response, and then we just parse out the results from the response. These are JSON formatted results. And then we can create some assertions against those results. So here I'm asserting that, well, we've got 200 OK, that was the status code, that it was JSON, that was the content type. And then I'm actually asserting that Lucy was the very first result that we got back, and so on. So very, very similar in the assertions, but just some of the other things that I had to do in order to invoke that extension was slightly different. But you can apply this over and over again, so you can develop your model and develop it in a test-driven fashion. And then this will give you the confidence that the stuff that you're writing is correct, but it also gives you that bedrock of assertive behavior that allows you over time to evolve your application. Okay. So all of the examples here you can grab on GitHub. There's an example of testing embedded and an example of testing the server extension. I can't imagine anybody doesn't have a copy of the book, because we've been forcing them on you as you turned up today. And you can grab hold of me, obviously, throughout the day here, but also on Twitter on Ian S. Robinson. Lots of Ian Robinsons out there, so Ian S. Robinson. Distinguish me from my brother, for example. All right, I've got a couple of minutes left. I can probably take one or two questions, and then we'll wrap up for lunch.
When you created those extensions, you started the JVM, so that server, in the embedded server process, it was same JVM that was serving the request. In the extensions, am I running those extensions in this server as well?
Yeah, so within the test fixture, we were creating a server, and we were controlling that server from within our process within the test. Nonetheless, we were communicating with it over HTTP, or effectively via the loopback interface.
But the reason I ask is, on there, with the REST API, I mean, you can throttle it, you can do whatever you want, but you could potentially have tons of requests coming in there.
Yep.
And JVM is a JVM, which is limited. So those extensions keep, because you're creating an extension every time a request is coming in.
Yeah.
Probably it's a stack of its own on a thread or whatever, however it's running it internally. That could grow very quickly, am I right?
Not necessarily. I mean, the JAX-RS spec allows for creating, I mean, effectively what we're doing is creating resources, creating instances of objects to satisfy requests. And that's a typical strategy for building web apps. It's very, very simple to create those objects. They get garbage collected very, very quickly. But what we're retaining, the long-lived objects, are the embedded graph database itself and the execution engine. Now, what we're not doing in the test is performance testing this app. We're testing its correctness, but I think there's a very different set of strategies for performance testing and ensuring that it can satisfy, multiple concurrent requests.
That's what I was doing, because if that garbage
Yep.
collecting, the other requests coming in will affect the performance.
Yeah. So this is testing the behavior of the application, but it's not testing any of the, what we might call the non-functional requirements and performance testing. Yeah. Graham, do you?
Yeah, I was going to ask whether you saw any significant shift in strategy with other application languages. So you were building a Rails app or something as well.
So
Mirror the second strategy of using an external database instance, presumably. Does that affect the testing strategies?
yeah, I mean, if you're developing on a different platform, very often you can't develop against an embedded graph database unless you're on the JVM. If you've got some other JVM-based language, then you can still develop against embedded. I think, unfortunately, those server extensions typically have to be written in Java as well. But actually testing the server product, although we were testing an unmanaged extension here, actually testing the vanilla version of the product and using the Cypher endpoints, for example, it's effectively the same strategy. Start up an instance, exercise it with an HTTP client, and assert the results. Yeah. I'll take one more question. And then.
So I have the luxury of not having built my product yet, and so I'm wondering, is there a single sort of optimal stack that you recommend, knowing that the only thing I know is I want to use Neo4j?
Right. Okay. I mean, if you're not constrained by existing systems and stuff like that, then my recommendation today is typically to use Neo4j in server mode. Use the vanilla version of the server, use the HTTP endpoints, the Cypher endpoints, and the new transactional endpoints in 2.0. That gives your client code lots of control over the transaction. You can make multiple requests, make decisions within, based on the results, and do all of that within the context of controlling the transaction. And only if you absolutely need to do something very, very complex or very performance sensitive would you drop down to developing the server extensions themselves. But I would recommend using server mode and just operating against the standard Cypher endpoints there. Does that help?
Yes, thank you.
Wonderful. Okay, I think it's lunchtime now, so hopefully that's been useful to you. Thank you all for coming along. Enjoy the rest of the day.